Welcome. In this demonstration, we're going to look at the sample distribution of the sample mean as well as the sample distribution of the sample proportion. So let's get started. What I have here is a partially filled out worksheet that tells us what we're working with. We're working with an ice cream shop, and we're going to first take a look at the sample distribution of the sample mean. So what we have is some population parameters here, and we're looking at the ounces per scoop in our ice cream shop. So let's say that the mean for the population for all ice cream scoops is 5.2 ounces, and that the standard deviation is 0.4. Now, as before, I'm creating a model that can be modified, so I'm going to highlight these in an obvious color here. Okay. Now I have my sample, and for my sample statistics in the number of scoops I'm going to take, I need to decide, well, what that number is. So again, I'm going to pick a number. We're going to take 2 scoops, and we're going to set this as well to that color. Now, the other thing I have to figure out is, does this meet the central limit theorem for the sample mean? Now, the central limit theorem essentially says that the sample distribution will be approximately normal if, and there's some criteria. And so for the sample mean, the formula for that, it's quite straightforward, but I am going to copy it in here. The formula for that is just n greater than 30. So we can plug this into a formula here to give us a yes or no answer. So we're going to use equals if, and we're going to say B8 is greater than or equal to 30. Then it's going to tell us yes, and if not, it's going to tell us no. So there you go, no. And if we put 30 there, it's yes. Now that no and yes doesn't show up very much, so I want to illustrate using the conditional formatting for this. So if we go up to our Home tab here and select conditional formatting, we can say highlight cells based on rules, and we're going to say the text contains. So light red fill with a dark red text, that will be for no. And understand we can change these, right? But for this one, we're going to say no. And then we're going to add another one for yes, same route, text that contains, and I'm going to say yes, but for this one, we'll make it green. I like these default configurations that they have, yellow on yellow, green on green, red on red. They're just quite visual. So if I change this to 2, it's quite bold, tells me nope, it doesn't meet the central limit theorem. If I change this to 30, there we go, it meets the central limit theorem. Now let's move on to the expected value. And what we're talking about is the expected mean of our sample statistics. So if I meet the central limit theorem, then the sample statistic the expected value of the sample statistic is going to match the population parameter, so this 5.2. So we can simply say equals B4. And then the sample error of the mean, or I'm sorry, the standard error of the mean, let's get that in there. The standard error of the mean is calculated by the standard deviation of the population divided by the square root of n. So we have that formula there. So again, we can calculate this. It's very straightforward, not a complex formula. Equals the standard deviation, so that would be B5 divided by the square root of B8. So the standard error of this sample mean is 0.07303. Okay? Now notice what happens to the standard error when I reduce my sample size. The standard error goes up. And of course, it doesn't meet the central limit theorem, so this value here is not accurate. In fact, we can change this so that we can make this an if statement. If B10 equals yes, then we want it to be B4. Otherwise, let's just put some dashes in there to indicate that we don't have an expected value for that. So now if we change that to 30, there we go. We have an expected value for the mean of 5.2, and we have a standard error of the mean. So, well, why are we doing all this? Again, we're looking at the sample distribution of the sample mean. So we can answer a question like this. What is the probability that the mean of the n-size sample scoops is A than B? So what we're going to fill in here is a less than or greater than. And so what we're going to do is a drop-down list here like we've done before. And so we can go up to our data, and we can use this icon here to use data validation. We create a list of less than, greater than. So our sentence reads something like, what is the probability that the mean of n sample scoops is less than, right now, less than, and I've got then there twice, so we'll take care of that. But I could say 5.1, right? Now, let's just clean this up here, and let's do it with the concatenate function equals concat. And what is the probability that the mean of the, what do we have? B8 is our sample size. Sample scoops is, and let's just put in H5. And we don't need that, so we're going to put in H6. And then we need an in quotation mark. So there we go. And notice this, I don't have my spaces here, so we can go up and correct this. So I need to put a space in between these. And I need to insert the word ounces. So does that read correctly? What is the probability that the mean of the 30 sample scoops is less than 5.1 ounces? And if we change this, we can say greater than 5.1, or we can say 4.8, or whatever the case may be. And we're actually changing the question itself. So again, these are ones that we'll alter. Okay, well, now it's time to calculate the answer. We're going to do this in 4 steps. And the very first step is a standard transformation, somewhat like we've seen before. The formula for that, when you're working with the sample distribution of the sample mean, is we take our value, so in this case 4.8, we subtract from that the population parameter, mean, 5.2, and then we divide it by the standard deviation divided by the square root of n, which is the standard error of the mean. So we've already calculated that. So now we can do this transformation here. And again, not a complex formula, so we need equals H5, H6 minus, I'm going to put these in parentheses. I always feel better having things in parentheses, especially around division, to force the grouping that I want. H, and then this would be minus B4. And we're going to divide that by B12, which we've already calculated out that standard error. So it would be negative 5.477. All right. So let's take a look at this now. to see, I'm prone to use these parentheses, but let's see what happens if I take the parentheses out. The number is completely different. Now, why is the number completely different? Well, because of order of precedence. Mathematically, we always do divisions first. And in this case, we don't want to do division first. We want to do the subtraction first. So it's always a good practice to force the equation to behave in the way you want it to, even when the order of precedence aligns with what you want to do. It's just always a good practice to use parentheses. So there you go. There's our correct answer. Now, the next step we're going to do is a cumulative probability distribution for less than. And you'll see why we're focusing on less than in a moment. And so this is simply the normal standard distribution function. And we're going to use that value, the z value, which is h9. That's our standard transformation. And then this is why we're using less than. It's cumulative. And it's a 1. And so what this is saying, let's change this to a percentage because that's what we're talking about. You don't need to see all that. So it's saying 0%. If we have a sample of 30, what's the probability that all the scoops, the mean, is greater than 4.8? But notice that we're solving it for less than right here. And we're saying, well, with a sample of 30, the probability that you get a mean of 4.8 when your population parameter is 5.2 and the standard deviation for the population is 0.4 is just not going to happen. It's 0% probability. Okay, but now we have to allow for that greater than, and so we're simply going to do an if statement for that, and this will show kind of why we're separating this out and doing this in steps. So if the h5 equals, let's go with less than, then we're simply going to stick with our h10. Otherwise, we're going to have 1 minus h10. Now, I'm going to illustrate this a little bit with you. Now, you can see it's nearly 100%, which is just the opposite percentage of that. So again, let's change this to percentage. Now, let's illustrate this. So what I've got is a normal distribution over here, and I'm just going to drag it over here, copy it over here. All right. And put it here. Now I don't have a scale on this, but our mean, right, is 5.2 for our population, and the standard deviation is 0.4. If we take a sample of 30, let's pick something that we have some percentages here. Let's say 5.1. Let's say 5.15. Okay, yeah, here we go. All right, so at 5.15 ounces for our mean for the sample, what we're saying is that there's a 75% chance that it's greater than that. So basically you would draw a line in this and fill in, it's all this stuff, all these possibilities for that normal distribution. Whereas the less than, you would draw that same line, but it's to the left of it. So what's the possibility that the mean would be to the left of that? Okay, so that's what these two mean in a visual sense. Now, what we're going to do here is simply put the answer in one formula. We've built it, but we'll put it in one formula here. So we're going to start with an if. And we're going to say if it's, let's see, if h5 equals less than, and I have to get the text exactly correct, which is a bit risky here. So then if the value is true, then I'm going to use my norm.s distribution, and I'm going to do that calculation. So that was the h6 minus the b4, all of that divided by my B12, and I want cumulative. Okay? So if it's false, meaning that it's greater than, I'm simply going to do 1 minus and have that same norm, the norm standard. Okay, and so now it's going to be same thing, right? H6, let's make sure we have our parentheses, minus the B4 divided by B12, and we want cumulative. So in theory, oh, I've forgotten a closing parentheses, and it kindly puts it in there for me. And let's set this to my answer color here. In fact, let's just set all of this right here to my answer color. And we want this to be a percentage. So now when I change this to less than, notice that that changes as well. And so we can play around with this. Well, okay, what if I just pull out a scoop? Now, it doesn't meet the central limit theorem, but what's the probability that the mean, so the actual measurement of that one scoop, is less than 5.15? It's a 45% chance. So now notice if we change this to 5.2, the mean, that these go to 50. And obviously it's 50 whether it's less than or greater than, because again we're dividing this in the middle, and the less than is to the left and the greater than is to the right, so the area under this, or the possibilities of these values falling in here along this distribution. So if you and I go to get a scoop and I get one scoop, what's the probability that my scoop is at 4.8 ounces? And there's a 16% chance. What's the probability that your scoop is at 5.4 ounces? Well, less than. Let's go greater than. There's a 31% chance. So I could get a small one, you could get a big one. The probability is there. So that is the sample distribution of the sample mean. Now we're going to switch to the sample distribution of the sample proportion, and you'll notice that I've set this up almost exactly the same, because many of the calculations are the same. Not the formulas behind them, because we're working with proportion, but kind of the steps that we need to go through to find this out. So we're dealing with our ice cream shop. We're talking about the sample distribution of the sample proportion. So now we have a proportion, right? And let's say that after a period of time, a certain proportion of buckets go bad, buckets of ice cream go bad. So let's say it's 12, and we want that to be a percentage. So not 1200, but 12. Excel is interesting in that. You put a number in and switch it to percentage. And even though you're thinking in your mind, I mean 12%, it interprets that as a whole number, and then you get 1200%. So just pay attention to that detail. Okay, so 12%, and this is a value that I will change. Again, I need my n. So let's say for this that I'm going to use 50, and these are the number of buckets in my sample. So I have my population parameter, my proportion, 12%, and I have my sample. I'm going to look at 50 buckets. Now, does this meet the central limit theorem for sample proportion? Okay, so this is different than the central limit theorem for the sample mean, and the formulas are different. In fact, this is a compound. This is an and here's what we have for that. If, let's see, let's park it down here. If the n, the number that we have in our sample, times the proportion of our population parameter is greater than or equal to 5, and n times 1 minus p is greater than or equal to 5, then it meets that central limit theorem. So let's do the calculation for that. And we'll do the same thing. We'll do an if statement equals if, slightly more complicated. Now our logical test has to be an and. So fortunately Excel has an and function. And the and function, everything you put in here, every test has to be true for this to be true. So the very first test is quite straightforward. It's n, so B8 times B4, that's my P, greater than or equal to 5. That's one of my criteria. And then the next one is, again, straightforward, but it's N, which is our B8. And now it's times, and I'm going to use the parentheses because, again, order of precedence matters. And mathematically, you would do multiplication first, but here I want to do subtraction first. 1 minus P, which is B4. If all of that is greater than or equal to 5, then I want that to return true. Okay? So if it returns true, then I'm going to say yes. Otherwise, I'm going to say no. So this is telling me if it meets that central limit theorem. So now let's lower that number to 25 and see that it says no. Okay? So we're going to do the same thing with this from the standpoint of our conditional formatting to trigger ourselves visually. Visual triggers are important. Now, what I want to show you, let's first of all demonstrate that that works. What I want to show you here is if I go up here to edit this and I manage these rules, oh, notice I'm not on the right cell, so Excel doesn't recognize this. So I can simply say this worksheet and it'll show me what cell these are in, as well as providing them. Now, if I select one of these and edit it, notice that the default was contains, but I can go here and say not contains, begins with, or ends with. So there's a lot of flexibility with this conditional formatting. We'll just leave it alone. I'll illustrate if I'm on the cell and I come up here and do the manage, it pops it up. It knows exactly what I'm talking about. Okay. All right, so we have to have the expected value here. And like for the sample distribution of the sample mean, the expected value for the proportion is going to match the population parameter if we meet that central limit theorem. So equals if B10 equals yes, then we want B4. Otherwise, we'll just put it in a dash. And let's format that as a percentage. And let's test it out. Change that to 25. Notice we have our dash there. Okay. Now, the standard error of the proportion, we need to calculate that, much like we calculated the standard error of the mean. However, the formula is different. And so let's take a look at that formula. So we're doing the square root of the proportion, the population proportion, times 1 minus the proportion divided by n. Okay, so we can do this here, equals the square root, and our number is B4. And I'm going to put this in parentheses again, remembering that my order of precedence, whenever I'm, especially around multiplication and division, and B4, so all of that divided by B8. And in my square root, and oh, it doesn't like that. What have I done wrong? Look at this, I don't have my multiplication sign. The little things. And there we go. We have our value here. And we don't need all those decimals, so let's get it down to 4 decimals, okay? And let's get this back to 50, so it's yes, we've got 12% as our expected value for our sample statistic, and our sample, our standard error of our proportion is 0.046. So now we have another question. What is, with a random sample of n, what is the probability that the sample proportion is A, B? So let's do the same thing that we did before. Let's enter our greater than, less than on our data tab, data validation. We'll insert a list. and we'll make it less than, greater than. There we go. And here we want a percentage, so let's change it to percentage. And we want to know something about the sample mean. So what if we said 14%? So let's modify our question here with that concat function. This is really helpful, especially if you're delivering something to someone else, to simplify it for them. So we're saying B8 is our number, and then this is going to be our greater than or less than. So let's say H5, and we want a space in there. And then the last thing is the percentage that we're using, which is H6. And we want, let's just leave it that way. 14%. No, let's put in the buckets went bad. And actually, we can put in, we can simply add I6 to this. So just illustrating that you can just keep stringing these things together as long as you want. Now it goes off the board here, but with a random sample of 50, what is the probability that the sample proportion is less than 0.14 buckets went bad? All right, so we'll be changing these in the future. We can set them to yellow. So now let's start answering this with our 4 steps. And the formula is in essence the same as for the sample mean, but of course the denominator is different, meaning that it's the standard error of the proportion, which we've already calculated over here. So we can do this formula equals H6 minus, and again my parentheses, H6 minus B4 divided by B12, and that will give us, and again we don't need all these, we'll get to 4, that will give us the standard transformation. And now we want to do that cumulative probability distribution for the less than. Okay? So we're simply going to equals norm standard, norm dot s, there we go, and it is H9, and we want cumulative. Now again, this will give us the less than. We'll change this to a percentage. Actually, we'll change all of these to a percentage while we're up here. So less than 67%, greater than 67%, because this line is only calculating the less than. So now here we want to allow for greater than. And this right here bothers me that we can't see all the greater than, so I'll simply fix that. Here you go. Equals, if H5 equals less than, then we want H10, otherwise we want 1 minus H10. So now we have the greater than. So with a random sample of 50, what is the probability that the sample proportion is greater than 0.14? We have about a 33% chance, so 1/3 possibility. Now again, we can build this all in one formula here. And so, and that will start with our if statement. And we're doing our same logical test that we had done before. H5 equals less than. Now this time, if it is, we're going to do that calculation. So we're going to do steps 1 and 2 in the calculation. And so we've got that norm, standard distribution, and then we're going to have to do the formula inside of here. So we have our H6 minus our B4, all of that divided by our B12, and we want cumulative. Now here it's 1 minus that norm, and we're going to just repeat what we had done before. So H6 minus B4 divided by B12, and we want it to be cumulative. And there we go. Now you've entered too many arguments. Okay, so let's go back here. So this is the norm, and somehow it's not. Oh, I did the inverse function. You got to pay attention to the details here. I want that function, and then it's going to correct the problem that I had with my parentheses. Okay, so there we go. We have the answer that we're looking for, and if we change this to less than, it should work. Yes, 67%. The probability that if we have a sample size of 50, that it's less than 14% went bad. So if we lower this to 25, notice it doesn't meet the central limit theorem. And in that case, we can still do the calculations, but we're not as confident that this is a normal distribution, right? Or approximately a normal distribution with our sample size. So we have to get our sample size up to somewhere where it meets that central limit theorem. And then we can play around with, well, less than 10, 30% chance, 33% chance. We can continue to play around with that. So there you go. That's a sample distribution of the sample proportion and the sample distribution of the sample mean. Now it's your turn to give it a try.